All right, we are at Living Energy Farm, and we are going to do a workshop, a series of workshops on electricity. The purpose of these workshops is so that you understand electricity as it fits into energy systems. Our goals are both environmental protection. We want to live with a lower environmental footprint, and we want to allow and encourage people to live more independently of centralized corporate interests. We have an audience here. I'm going to be speaking to the camera, so you can't see the audience. You can only see me. So we have to start out with a standard disclaimer, and we might put this in print because we put it on our videos. Electricity can be dangerous stuff. It can shock you. It can electrocute you. It could burn your house down. So if you watch this video, you are not an electrician. This purpose of this video, purpose of this workshop, is educational, not to make you, not to allow you to do things that your skill level doesn't allow you to do. So if you're going to do work with electricity, you either need to have the skill or you need to hire somebody who has the skill so you don't burn your house down or hurt yourself. And we are not taking responsibility for any of your behavior. This is for educational purposes only. So all of that said, so the first thing to understand about electricity, at least in a renewable energy context, is that it has been given far too much weight. The reason for that is pretty simple. Electricity is a bulk commodity, whether it's coming down the power wire or sold these days as with solar electric panels. So this is a solar electric panel. We just refer to it. Photovoltaic is the name. Of course, they make them much larger. But we often just refer to these shorthand as PV. So if you put a bunch of these PV panels on your roof, you can grab this wire. See how easy that wire bends? Well, this is really the reason that these things have so much political clout, is because fairly unskilled crews can put them up on somebody's roof, run it down to an inverter. The economics, the ecology of it doesn't make any sense often, but solar thermal systems, conservation, cooperative use, those are what matter, both from a financial standpoint and from a environmental standpoint. But these are what has the political cachet because it's like cookies or pizza or anything else. Somebody can sell it to you. And particularly compared to thermal systems require pipes and wires, and those are harder to install. That wire can be bent all over the place, so it makes PV panels easier to install. And you might think, okay, well, it's an academic point. It's not an academic point, nor is it a recent point. I could point you to buildings within 20 miles of where we sit, built back in the 1970s, where they would build a big, elaborate building and then put solar thermal stuff on it or solar electric without insulating the building. It's crazy. It happens all the time. In fact, it's the norm. It's stupid. Well, if you want to be stupid and you want to be enslaved to corporations, that's your business. But if you want to reduce your environmental footprint and reduce your level of independence, here's what you need to know. First of all, what you're building where is what matters, and context, particularly shared resources, is what matters most of all. Very simply, solar hot water has a better payoff than solar electricity. But solar hot water, a good system, if you're living by yourself, is going to cost you $3,000. A good system for 20 people would cost $6,000. So the per capita cost of thermal systems tends to collapse as the number of users grows, at least within the order of a few dozen. So this is the reason I think I'm probably not rich and famous, although there might be a lot of reasons for that. But in any case, for decades now, I've been standing up in front of people and saying that cooperative use is the magic solution to all of our environmental problems, and mostly people don't want to hear it. I'm going to keep saying it. I'll die one day, and people still won't want to hear it. But that's what I'm going to keep saying because that's what's true. Economically, ecologically. Solar thermal, space heating. If you take a big house and you have people sharing that house, the ratio of interior space to exterior space is such that the bigger house, a community scale house, has an innately environmentally much lower footprint. So I could talk about that for hours, but I'm not gonna. I'm just gonna tell you that context and renewable, cooperative use, context, what you're building where, it's not the house on the mountaintop. It's living, cooperating with other people near the services and energy systems and resource systems that support you. That is 90% of the battle. If you get that wrong, these things do more harm than good, and in fact, they generally do more harm than good. But if you get that part right, and then you do a good job with conservation, again, this is not a green building workshop. We use a lot of straw bales around here. Take a new house, lean straw bales against the wall. Take an old house, lean straw bales against the wall. 18-inch thick walls, they don't cost any more than a normal house. If you get those two things right, good context, good cooperative use, good conservation, you've taken down 99% of your struggle, and then this becomes a magical, powerful energy source. Okay? If you try to invert that, to take shitty buildings and put PV panels on them, even solar thermal on crappy buildings or on buildings that are out separated from the services that support them, that's not environmental. Okay? Nor does it make financial sense, although a lot of people do a lot of stuff because they have the money to do it. So we had our safety preamble, and then you just had your political preamble, which is that electricity is not the most important thing. But when you do get down to the point of, hey, I want to live on a self-sufficient homestead. Hey, I want to know how to make my own energy systems. Hey, I want to help other people do that. That's what we're going to talk about now. So let's talk about electricity in particular. So electricity is very complex, far more complex than I understand. I have had friends who have dabbled in, or who know how to design radios from, the whole damn circuit. I don't know how to do that. But I've dabbled in that enough to know that electricity is extremely complex. Okay, that's fine. What runs your cell phone is the same thing that makes lightning pop across the sky, sort of. They're both electricity. But we're going to break it down to a simple metaphor. The thing you have to understand about the metaphor is it's a metaphor, and it does not apply. If you're going to go build computers, this metaphor is going to fall apart pretty quickly. But for what you do around the home, this metaphor is going to work just fine. So our metaphor is we've got a pipe coming from, let's say it's a big lake, a big reservoir. Water is scooting down this pipe, and it's hitting a turbine. A turbine is just something that spins, right? And that spinny little turbine is going to generate energy. Okay? All right? So just at a basic intuitive level, the more water we move through there at a higher pressure, the more work we can do, right? Got it? Okay. So in terms of electricity, what do we think the pressure represents?
I think the volts.
Voltage. Good job. Okay. And naturally, if we take the pipe as a constant, let's say that's a 2-inch pipe, whatever size pipe it is, the more pressure, the more water's going to go through there, right? Okay, same's true with electricity. The more you increase the voltage, the more electricity wants to go through there, depending on how much electricity is available. Some electrical sources have a finite reserve, some don't. When you're hooked to the grid, you have a near finite supply, or just a huge supply. Okay, what do we think volume is?
Amperage.
Amperage, okay. So volume and pressure are related, voltage and amperage. So with your little turbine, in terms of how much work it can do, higher pressure means more work, higher volume means more work, okay? But in theory, you could have super high pressure and low volume and do the same amount of work as super high volume and low pressure, right? Those two kind of trade off against each other. But in terms of wiring, so this pipe is an electrical wire. The voltage, the amperage is what makes for heat. So if in electrical systems, if your pipe is too small, your wire is too small, you're going to get heat. And heat is not a good thing, not too much heat. So when they design electrical systems, what they're thinking about, so they're going to put a 1,000 horsepower motor in some big industrial something. They do a lot of very careful calculations about how much power they need down here, how big of a wire, how much heat is going to be dissipated off of that wire while that motor's running. That's really what you want to do, is keep things from overheating, okay? The voltage is what can do harm. So your body runs on electricity, right? A milliamp is 1,000th of an amp, which is not much. It's very little electricity. 15 milliamps through your heart muscle is what will kill you dead. So a tiny electrical shock, if it can get to your heart muscle, can kill you. The reason all of us have received some electrical shock, some of us more than others, and not died, is because that electricity didn't get to your heart muscle. But if you think of your body as a pipe, the higher the voltage, the more electricity is going to try to push through your body And that's the reason higher voltage is more dangerous, right? If you're touching something like a 12-volt source, there's not enough voltage to push enough electricity through your body to do you any harm. But as that voltage goes up, the pressure goes up, that electricity is wanting to go somewhere. And that's what makes it more dangerous. Safety-wise, at least in terms of code, 48 volts and below, is there a mathematical symbol? Yes, less than. That's a less than sign. Safe, sort of. Is that a less than sign? Did I get it right? It's been so long since I did real math.
Yeah.
Now, you shouldn't take that too literally. It's a benchmark. And the reason you shouldn't take this too literally is my sister's ex-husband, a guy she married many years ago, worked on stage lighting. They run stage lighting and telephone, the old copper wire telephone systems. They run those at exactly 48 volts because everybody thinks 48 volts is safe. Well, he was up in a metal rack one day, sweating like a dog, holding on to a metal bar, and one of those 48 volt stage light wires got him right on the forehead and killed him dead as a nail. Killed him dead. 48 volts. So 48 volts is mostly safe. Some of you guys have helped me do some arc welding. Those are less than 48 volts, 24, that range, volts. Mostly 48 volts is pretty safe. Household wiring is up 120, 240. That is not safe. You do not want your hands on a household wire. The telephone systems, the reason they do 48 volts is for safety. Like if you're ever in a house with a copper wire phone system and you touch the wire, you might get a tingle, but it ain't going to kill you. So 48 volts, as far as code is concerned, is what's the safe level. But you just want to keep it in mind. Like if we string together 3 solar panels and we've got 90 volts, you're not going to touch those wires, right? If we got one 24-volt solar panel, you're not worried about it. All right, so there's a valve in here in our pipe that's going to determine how fast the water goes through. And of course, the pipe itself has some friction in the pipe. As we close this valve, it slows down the water. If the pipe is too small, that creates friction. What is that in electrical terms? Resistance. Okay. And we'll draw so voltage is V, amperage is A, resistance is a little horseshoe. Okay, resistance. So if we're measuring, so there's a mathematical equation, which I can never quite remember actually, even though I do a lot of electrical work, that relates resistance to these other two. You don't actually ever need it hardly very often, but what you do need every day is your total energy, which is voltage times amperage equals watts. Okay? That's the total energy that this turbine can deliver you, and that equals W. And everybody gets that kW, kilowatts, is 1,000 watts, right? That's easy. Okay, so that's the total amount of work that thing can do in a particular instant. But now if we're talking about the amount of work we can do in half an hour, 2 days, that's over time. Okay, that becomes watt hours or kilowatt hours, okay? Or kW, watt hours, kilowatt hours. Okay. So, when the electric company sells you electricity, when you're connected to the grid, they measure kilowatt hours. That's what they measure. If you use 2 kilowatts for 2 hours, how many kilowatt hours? 2 kilowatts for 2 hours.
When is 1 kilowatt? 1 amp.
No, kilowatt hours. How many kilowatt hours? 2 kilowatts, 2 hours.
4.
4. There we go. 4 kWh. And that's how much you would get charged for. The standard billing around here is around 10 cents a kilowatt hour. Okay, get it? We'll do some more on that. Don't worry. All right. In fact, let's do some more now. Let's give you another, because there's a battery thing. Batteries are generally measured in AH, which is amp hours, right? But the problem with AH, or the limitation, is there's no voltage and there's no time. Well, there is a time, actually. There's an hour. So the battery set we have over here is 100 amp hours. And that's a 12 volt, nominal 12 volt. It actually runs from 10 to 16, give or take. How do we make that into something that tells you how much actual work that thing will do? Right? Well, first thing we do, we're going to use 12 as our benchmark because even though the batteries swing around a bit. So watts, where's watts? Watts is volts times amps. Total energy equals volts times amps. If you know that one equation, you can take care of most of what you need to do, electrically speaking. So volts times amps. All right, so we got 12-volt system at 100 amp hours. How many watt hours is that?
So you said 12 volts.
Huh?
1200.
1200 watt hours, yes. How many kilowatt hours? 1.2. All right. So our battery system, all right, let's go to another piece of paper. 100 amp hour at 12 volts, right? Okay. That equals 1200 watt hours, right? That's what we just did. Okay. Which equals 1.2 kilowatt hours. Got it? All right. Now, let's play with some electricity. Or maybe we'll do this in another class, but I'll just refer to it now. There are lots of different kinds of wiring and whatnot. That is something that, well, you need to ask somebody who knows how to do it. We'll come back to that. I'm just thinking about that because, in terms of setting these systems up, you do have to get the wiring right coming off your batteries and whatnot. So I am actually plugged into our, so this cable, at Living Energy Farm, we have high voltage DC and low voltage DC. We do what we call daylight drive. 90% of our electricity never goes through a battery. It goes straight from the PV panels, these panels, to a motor. Then 10% of our electricity actually goes into the batteries, and then that becomes a kind of voltage stabilized 24/7 power supply. And most people, they've been convinced to buy bulk commodities. Here's more cheese pizza. Here's more chocolate chip cookies in a bag that came from a corporation. Well, that's what energy is. Now, given this speech, I'm not going to give it at any length, but right behind me is our solar thermal storage fridge. So this fridge, 10 to 45 volts, runs during the day, chills down, and then stays cold because it's well insulated. Okay? Let's actually back up and do that. Let's just figure out, so if that fridge is using, right now it's running on 24 volts. We don't know how many amps though. Never mind. Let's work with something we can actually measure. So we just got these fans in the other day. I have for months now been working to try to find a brushless fan. So do we have a timekeeper, by the way? Do we know when we started?
It's 2:11 now. I thought that we started at 2.
Okay.
Yeah.
All right. So just let me know when we get close to an hour. Okay. So I'll show you what a brush motor is shortly. This is actually a brushless motor. When it comes to motors, DC motors, so AC electricity, DC electricity. AC electricity travels as a wave. It's drawn as a sine curve. DC electricity is just drawn as a line, like that. Okay? What comes out of a photovoltaic panel, or what comes out of a battery, this is connected to the battery, these are both DC electricity, right? Straight line. When you're looking at a meter, if you're going to play with electricity, this meter is very cheap. Better meters cost a little more. But we got the V with the straight line, that's DC voltage. And we got the V with the squiggle, right up there, AC voltage, right? Okay? I wonder if I put this up if the camera can see it. Now, one funny thing about these meters, or one thing you have to understand, so your black wire is going to go on your common pole. Generally, they've got like, hey, this measures everything pole, and then if you have a high amperage pole, that's going to be separate on your meter. So if you put this in the, hey, that measures everything pole, and we come over here and we set that on 2 volts, get our leads. Tell me what the meter just did.
Said 1.
Well, what it did though was it got confused. You know why? Because we're trying to read 2 volts. And this power source is probably about 12 volts right now. We got it on the wrong scale. So these scales are 200 millivolts. That's for reading tiny little electronic stuff. I set it on the 2 volt scale and the meter said, too much. So it freaked out and gave you a silly reading. If we go up to the 20 volt scale, then it'll give you an actual reading. At least I hope it will. Is it working? 12.4. Don't worry about decimals. Okay. All right. So now there's a black wire and a red wire. What happens if I put the red wire in the middle and the black wire on the outside?
It's 12.5.
Okay. So if you don't already know your polarity, that's how you figure it out. If your black wire is on common and your red wire is on the little thing that says, hey, I measure everything, and you put your red wire on your positive voltage source and your black wire on your negative, you get a positive number. See that? Generally speaking, with AC and with DC, your positive is usually hidden away. The reason for that is like, let's say this is a light fixture and you're screwing in a light bulb. If you got your fingers on the metal part of the bulb and it's touching this outer rim, you want that to be the negative. Because in AC world, the negative won't shock you. At least it shouldn't. So you put the positive places where it's harder to get your finger to. You wouldn't want to do that with a high voltage household current source. But this is 12 volts. Not going to hurt me. Okay. So what I've done here is I have measured, well, so I'm going to move that over to amperage. Now, a lot of the good quality meters don't actually have a high amperage scale because it's easy to destroy the meter with a high amperage scale. So this is a 10 amp scale. With AC electricity, you can measure the amperage without breaking the wire. With DC, you actually have to break the wire. So see what we got here. We got a cute little Chinese fan. We are going to sell these fans. They're good little fans. They have a brushless motor. Brushless motors last half of forever. Industrial brush motors last a long time too. But a small motor, like a little fan like this, you're way better having a brushless motor. There's a bunch of little truckers fans out on the market now. Some of those might be okay, but they're going to burn out in a few years. And you're not going to be able to fix them. This should last for a long, long time. The plastic, it's plastic, so don't drop it, don't run over it. But it's got a really good motor in it. So we're going to sell these. I think it's a good fan. All right, now I'm going to turn this fan on low. Now you see the circuit is broken. You see what I've got going on here? I've got my DC coming in, hitting the plug. I've got one wire straight in, and I'm going to put the meter so it finishes the circuit here. Woo! Got it? All right, now tell me what that meter is telling you.
This is 0.3.
0.3. All right. Point 3 amps, right? All right. And we measured our voltage at 12.5, but let's just call it 12 because I don't want to deal with decimals. Times 12 volts equals how many watts?
36.
No.
0.3.
Over.
4.
Oh,
Because of the decimal.
3.6
It's
to be
3.6,
exact.
but he doesn't do decimals, so it's 4.
3.6 watts. Okay? That's not much. Cool. So we are, can I do commercials here?
Sure.
Living Energy Farms Iron Sun Box, a little 10 amp hour battery, nickel iron battery, lasts as long as you live. It will light up your cabin all day long and then run this fan all night long. I did it just the other day, and in the morning the voltage on that box was still at 13 volts. That's a $300 kit that'll outrun most of the lead acid kits. All right, now we're going to do something even fancier. All right, let me get my plug set back up here. Should have got some gator clips. And now I'm going to punch the second button. That's your second speed, faster button. Okay, now what happens if I get stupid here and touch these wires together?
It's gonna spark.
Okay, but what's happening electrically speaking?
Oh, it's creating one of those.
Short circuit,
Yeah.
but in terms of our pipe, I got a big pipe with no valve in it. A lot of electricity is going to want to come through. What happens when a lot of electricity wants to come through? Well, the pressure is going to stay the same. So where the battery's set, the voltage is going to not move much. What batteries have is amperage, crap ton of amperage. When you go to start your car, those starters often will handle anywhere from 150 to 500 amps. hundreds of amps. That's the reason your starter cables, I mean, on a modern car, the starter cables are about that big. The old-fashioned trucks, you'll have starter cables that big around because they have to handle that huge amperage flow. So if I was dumb enough to stick these wires together, it's like that's a dead short. There's all those amps in that battery is going to try to go through the wire, and luckily we have fuses and circuit breakers over there that will either trip off or burn out to keep this wire from setting itself on fire. Okay? But that's what they're there for. Amperage is what makes heat. Remember that? We'll go back to that point. Okay, now let's see what we get.
Yeah, -0.5.
0.5. Yeah, the negative and positive doesn't matter in this case.
No.
All right, 0.5 amps times 12 volts equals 6 watts. Woo! 6 watts. Everybody got it?
Yep.
All right. All right, let's put it up on full speed. Now let's see what we get.
.7.
0.7. 0.7 amps times 12 volts equals, can I do that in my head?
8.4.
8.4 watts. All right, now, so a nickel iron battery set will deliver, so safety-wise, I'm going to unplug that. So now this wire is not live, so when I put it down, it's not going to make a bunch of sparks. I like these fans. Nice little fan. Nice little fan. That fan will keep you cool all summer long with a tiny little electrical system, and it will run for many years to come, we hope. But let's say, oh, you know what I should have done? I should have set up a lamp. But lamps, the bulbs come with wattage on the bulbs, although they're not always all that accurate. All right, let's take, so our little battery sets, our cabin kit is rated at 110 amp hours at 12 volts. Actual delivery is 12 amp hours at, 12 volts. Got it? How long can it run that fan on low speed?
Oh dear. That's a lot of math.
Not so bad. All right, 12 volts times 12 amp hours is 144 watt hours, right? Okay. All right. So how many watts does, when this thing's on low speed, it's running at 3.6, how many watt hours does it use in an hour? That's a stupid question. 3.6, you got it. Okay. So 3.6 watt hours, we could say per hour. That's per hour. Yeah. So if we got 144 watt hours, and this pulls 3.6 watt hours per hour, 144 divided by 3.6, right?
Forever.
Long time. I want to know, actually. Somebody got a little machine. Do it, if you will. 4 divided by 3.6.
40.
40 hours. So our smallest cabin kit by itself will run that fan for 40 hours with no power coming in. Okay? Now if you've got this out there every day collecting sun, that means it never goes out, is what that means. All right. Let's crunch the other ones just for the fun of it. All right. 6 watts, so 6 watt hours per hour, right? Hour. All right. 144 divided by 6 is 24, I bet. Because 12 times 12 is 144, right?
Mm-hmm. Yeah.
24 hours. Okay. 8.4 watt hours per hour. Somebody do that math.
17 hours.
17 hours. All right? Starting to get some idea of how to figure out your loads, right? Do we need to keep going with that? I mean, the math is pretty simple. you know, if you had, you can either, so I'll tell you a DC LED bulbs. Okay, so let me grab a light bulb. Actually, could you give me one so I don't have to?
You can get it.
I should have brought a lamp. They're up there in the far corner. Far corner behind, yep, right there. You're going in, just keep going. That's them. Yep, that's it. Okay, DC LEDs. So this is called a corn bulb. So I'll tell you a few things about LEDs. So an LED, originally, like anything that has a light in it, like I don't know if you noticed when I plugged in this thing. LEDs are traditionally used as a signal, so that's an LED. Tells you that the plug is plugged in. The reason they use them this way is because it uses a tiny amount of electricity. So LEDs have been around for decades, but you can't light up a room with that little thing. Nobody ever thought, let's light up a room with it. Yeah. So back starting some years ago, people started taking these little tiny little pinpoint LEDs, and they started bunching a bunch of them together and actually making light bulbs. And then they developed the technology further. So what these little yellow chips in here, they took that little pinpoint LED and they spread it out so that whole little yellow thing in there that's one LED. They made the surface bigger. An incandescent light bulb takes a 100-watt incandescent light bulb takes 95 watts and makes it into heat, and takes 5 watts to make into electricity. They are 5% efficient. A CFL, compact fluorescent, or any fluorescent, is about 25% efficient, so it's a lot more efficient. These are like 80, 90% efficient. They're really good, comparatively speaking. The weakness of LEDs, so most things, like a normal incandescent light bulb, and it's true for most motors as well. So I was going back, remember I was talking about shorting the wires together? So like when we're running the fan, like the fan itself is like has the valve partly closed in terms of the amount of water going through there. And when you short circuit, it's like you open the valve all the way up and a whole bunch of water tries to come through there, which could overheat your wire, right? A lot of the old-fashioned incandescent light bulbs were actually self-protecting in that when they were sitting there dead cold, the valve was way open, but as soon as they started to heat up, the actual heat closed the valve down. In other words, a cold bulb draws this surge of electricity, but the instant it heats up, it drops off the surge, and that's your actual flow from there on out. Okay? That's with an old-fashioned incandescent light bulb. A lot of motors act the same way. You throw the switch, so a motor that draws 10 amps might have a 40 amp surge on it if it's an AC motor. And this is part of the reason AC systems are inherently inferior in every way. Mostly they're inferior because PV panels make DC, but one of the reasons is the start surge. So if you try to set up a wood shop and you've got a 1-horse motor on your table saw, and that's a 1-horse motor is going to be 1,000 watts, 1,200 watts, you're going to have a 2,000 watt inverter to handle that because of that start surge. Now the inverters themselves have a start surge built into them, but that start surge is a big deal. Where that matters for LEDs is they actually are one of the only electronic devices that have an inverse heat relationship with them. The problem with LEDs is as they heat up, the valve opens up, the resistance drops. And then they try to let more electricity through, which if it's not controlled, becomes a positive feedback loop, which destroys the LED. In other words, if you take a single LED and you hook it to a voltage source that's higher than what it's made to handle, you throw the switch and it just, the first little bit of electricity that hits it warms it up, which lets a little more electricity through, which warms it up more, which lets a little more electricity through. All that takes about a second and the LED just burns out. Okay? What that means in terms of light bulbs, every LED has a little computer chip in the bottom of it, a little circuit. The different manufacturers use different circuits. This particular light bulb has a pretty poor voltage tolerance, voltage fluctuation tolerance. We don't buy these anymore. We are buying more expensive bulbs that we're now selling through Living Energy Lights that have a very good voltage tolerance. Basically, for an LED bulb to work well, they have to put the time and effort into designing an electric circuit in the body that they're going to build into the base of this bulb that's going to keep that valve set at exactly the right place. That as that LED heats up, that valve is going to make sure that it doesn't overheat. That's the difference between a cheap bulb and a good bulb, basically. Although the bulbs we have now cost the same amount as this bulb, except they're better quality. The difference between a good quality bulb and a crummy quality bulb. So these bulbs, it says right on the side of it 12 volt. The thing with LED bulbs I have found is that the wattage varies significantly from the rated wattage. I mean, so this is like going to be a 4-watt bulb. It might pull 3 watts, it might pull 5 watts, you don't know. So if you're, for planning purposes, if you're thinking about how many light bulbs, you could use the numbers that the manufacturers are giving you, but you should be aware that the world doesn't necessarily, that what the manufacturers tell you is not the way these things are really going to perform. But just like we did with our fan, if you were thinking about, so it's about almost 10 to 1, but 8 to 1 is a safer number, the light output of an LED compared to an incandescent bulb. So if this is a 4-watt LED bulb, that's about what it is, it's going to have the incandescent lighting capacity of a 32-watt incandescent bulb. Because I think for most of us, those of us with any age certainly kind of have in our heads like, oh, I know what a 30-watt bulb will do, and a 100-watt bulb, well, that's really bright. You can kind of do the translations when you're doing planning, and then you can go back just like we did here. So if we've got a 3-watt bulb, you know how to do that. 3 watts in an hour is 3 watt hours, and then you can figure out how many 3-watt hour, how many bulbs your battery can run, right? Everybody get it? Should we go through that, or is that too simple? We know how to do it. Everybody following me? So you can plan. You can think about how many light bulbs I'm going to have. So we're selling now 3-watt bulbs and 7-watt bulbs. You could think, oh, I'm going to have 2 3-watt bulbs and 2 7-watt bulbs in my cabin, and I want to run the fan all night. You could just crunch the numbers, and you would get something pretty close. You'd be closer with the fan than you would be with the light bulbs. The light bulbs, for some reason, don't bear much resemblance to their what they say they will do.
Do you know the lumens on those bulbs?
I don't speak lumens, but that's the 8 to 1 thing.
Okay.
So whatever the lumens is on a 32-watt incandescent bulb is going to be similar to a 4-watt.
Okay.
Now there's also the brightness. See, that's a whole different number. Lumens is like total light. Brightness is the color of light. I personally, it's another thing that I just don't care about. But they are now, you can buy LED bulbs in any color. At least they generally give 4 color ranges. So if you want that calm yellow light, you can get that. What we have right now is the brighter light in terms of what we're selling. And as our business grows, we will offer more of the different colors. But we can't afford so much inventory. But you can buy them in any color you want. Because some people are really sensitive to, oh my God, that blue light. And other people are like, yeah, whatever. I'm in that yeah, whatever category. So. But if you want that yellow light, you can get it. Okay. So let's talk about how to relate this back to solar panels, our favorite subject. So what I did was I took every solar panel has a set of numbers on the back of it, every PV panel. Unfortunately, they are not consistent in terms of what they tell you and in what order they tell you. But you can usually figure it out if you're paying attention. So this is just numbers copied off the back of that thing. So Pmax 5 watts. What do we think that means? Maximum power, right? So what that's telling you is that under optimal conditions, this panel will put out 5 watts. That's what it's telling you. Okay? VMP, 8.6 V. Voltage maximum power. So what that's telling you is that under optimal conditions, you will get as much as 8.6 volts out of this thing, but don't count on it. IMP, amperage at maximum power. Okay? So at maximum power, you could get 0.58 amps at 8.6 volts, which is close to 5 watts. VOC. V is always voltage. I'll give you that clue. OC is open circuit. So anytime you have an electrical circuit, the voltage will tend to be kind of high, and as soon as you load it down, it's just like driving a truck uphill. You're scooting along, you got your pickup truck loaded down with something, and you're doing 70 miles an hour, and you hit a hill, and the truck starts to slow down, right? Well, electricity does the same thing. When you have a battery or a PV panel and there's no load, there's nothing using the electricity, the voltage goes up. And as soon as you start using the electricity, you're going uphill and the voltage will drop some. Okay, that number usually is not as important as your VMP number, but that's okay. ISC. Was that ISC or IMP? Did I write that down right? No, that's ISC. Yeah. I don't remember this stuff either. Don't worry. Amperage, short circuit. All right, so what these two numbers are good for, a lot of things have a maximum operating voltage. Like most of the wire that they use in the wall of your house has a 600 volt maximum operating voltage. A lot of these PV panels will have a maximum operating voltage. Okay, what that means is that basically just how thick the insulation is, right? That's what this VOC number is good for. Because when you start stringing panels in series, we'll talk about series and parallel in just a second, that's the number you want to pay attention to. We would not want to put so many of these panels in series that we got something above 600 volts VOC. Amperage, again, that's kind of your worst case scenario. You remember amperage is what can melt a wire? Well, if you put enough of those panels in parallel to get too much electricity for the size of the wire, that's your worst case scenario in terms of melting your wire. Generally, you can look at panels. Panels are always going to be nominal 6 volt, 12 volt, 24 volt, and now these days they've got a bunch of wacky panels that don't conform to any of the old standards because they're all doing grid tie. All right, but those are your DC voltages. When you go up from there to industrial stuff, it goes 48, 90, 180. All right, but in PV world, this is mostly what you're dealing with, is those three. So what do we think this one is?
It's nominal.
Nominal 6 volt, even though the voltage maximum power is 8.6, quite a bit higher than 6, but that's what it is. It's 6, and that's just something you got to know. Basically, what's going to happen, actual, 8 or 9 volts on a 6 volt panel, 16 to 20 on a 12 volt panel, and 30 to 35 on a nominal 24 volt panel. Okay? That's the actual voltage on what these panels that are calling themselves, so that nominal, this is nominally a 6 volt panel. If you go to a solar supply store and say, I want a 5 watt, 6 volt panel, they will hand you this one. Even though the actual voltage, the voltage of maximum power, the voltage on a bright sunny day could be as high as 8.6 volt under load, or even as high as 10 volts with no load on it. Mm-hmm. It's nominally a 6 volt panel. Okay? All right, let's talk about series and parallel. Series and parallel applies to both energy using devices as well as energy producing devices. Energy using things are called resistors and are drawn as a squiggly line like that. That is the electrical symbol for anything that uses up electricity. Okay? So, there is no consistent symbol for batteries or solar panels. But you remember with our red and black wires, they have a positive side and a negative side. Okay? Those are 3 PV panels. They each have a positive, they each have a negative. Okay? Now with resistors, if we do this, those 2 resistors, one after another, are in series, right? What tends to happen, and I shouldn't give the math here because I never remember it very well, but your resistance, I think it squares, that's my memory, but I might be wrong. It doesn't matter, I never use it. If the resistors are in parallel, like this, okay, now this is a little bit more complicated drawing. All right, let me finish the circuit. So electricity always has to go in a circuit, right? So with the resistors in parallel, in series, the electricity goes along and hits a resistor, kind of gets tired out, oh my God, then it hits the next resistor and it's really tired out by the time it gets back here. I'm pretty sure it squares. So if you got a 2 ohm, ohms is a little horseshoe thing, you got another 2 ohm resistor, that's 4 ohms worth of resistance, okay? I think that's true, I might be wrong, but that's what I remember. With these, half the electricity gets to go up here and go through this resistor, and half of it gets to go through this resistor to complete the circuit. So it goes by square root. So this circuit will pass, if these resistors are the same, this circuit will pass a lot more electricity. Okay? Now for electrical sources, it's the same general idea, although the drawing is going to get more complicated. Okay. So if I'm tying all my positives together, okay, this is parallel. That's parallel. And the negatives, on a schematic, whenever one wire goes over another, you do that little bump. It just shows you that those aren't touching each other. It's a little bridge. Okay, this is parallel. Okay? Now for an energy creating source, and this could be a battery or PV panels, whatever, your wattage is always going to stay the same, regardless of whether your circuit is series or parallel. Parallel, put it down here. Put it on another sheet of paper. Okay, parallel.
Like 40 minutes FYI.
Okay. Okay. So in a parallel circuit, the amperage adds up and the voltage stays the same. Okay? So what's happening in this circuit, let's say these are each 24 volt panels, but they're tied together in parallel. So the voltage coming out of here hits that wire, the voltage coming out of here, that wire. So those two wires is still 24 volts. But we have the power output of all three. Let's say these are 100 watt panels. So we've got 300 watts because we tied them all together, but it's still at 24 volts. So your wattage is going to stay the same, but your amperage is going to add up. Okay? Now with series, okay, same three panels. We start out like that, right? Okay. Just like with the resistors, they go in a row. Okay? Positive, negative, positive, negative, positive. So what you end up with at the end of the line is a positive and a negative, just like you had up here. Okay? The difference is that so with a series circuit, the voltage adds up and the amperage stays the same. With a parallel circuit, the amperage adds up and the voltage stays the same. In either case, the total power output is the total power output. So if we've got three 100 watt panels, we got 100 watts, but in this case, let's say they're 10 amps each. We're going to have 24 volts at 30 amps with the parallel circuit. 10 amps plus 10 amps plus 10 amps. With this one down here, 24 volts at 10 amps, although I'm screwing up my numbers here because that wouldn't be 100 watts, but in any case. Down here, if that's 24 plus 24 plus 24, it's 24 times 3. 72 volts, but still at, what did I say, 10 amps? So the total power is the same, but you can add up the voltage or you can add up the amperage, depending on what you're trying to do, right? Okay?
When do you want to increase the amperage and not the wattage?
Good question. See this here motor? So this is a 1/3 horsepower, 24 volt motor. Now what I normally do in workshops is I make people get on the internet and find this stupid little manufacturer's number here and look up the specs on the motor. That would use up a bunch of time, and I don't have time to do it right now. So we're going to shortcut it, and I'm going to explain it. So this is a 1/3 horse, 24-volt nominal motor. Now, one of the nice things about DC motors is they tolerate a lot of voltage variation. But that motor wants 24 volts. It wants about 350 watts, 360. I forget the exact numbers, somewhere around there. So for that motor, we've got 24 volts, 360 total watts. How many amps does it want? Come on, y'all keep the calculator going.
Yeah, 15.
It wants 15 amps. What happens if we don't give it what it wants?
It won't work.
It won't work very well. And if you really don't give it what it wants, it won't work at all. You have some flexibility. With all of this DC equipment, you can overload it, underload it, you can push it. And having some experience with this stuff lets you know how far you can push it. All right, this exact motor, this is not a theoretical motor, this is a real motor. We ran irrigation pumps with this motor for many years. And the 2 PV panels we were running this thing off of were they had 24 volts, and they were 100 and, God, what's the wattage on those panels? I want to say they're 160s. What would that give me in amps?
So 160
No, they're bigger than that. They're closer to 200. They're 200 watt panels.
divided by what?
Divide 200 watts by 24.
That's 8.3.
8.3. That's pretty close amps. All right. All right. So we have 2 panels, and this is pretty close to what we actually have. I don't remember the exact numbers, but it's the thing with being a DC electrician. You get lazy because you don't have to know exactly what's working. It all works so well. But in any case, so we have 2 panels out there. They are rare panels that actually put out 24 volts instead of just saying they're going to put out 24 volts. 210 watts, that's what they are, but we're going to say they're 200 watts. 8.3 amps. How do we make those 2 panels run this motor?
Do the parallel.
Parallel. If we put them in series, we'd be up at 48 volts at 8.3 amps. The motor would run, maybe, but it wouldn't be very happy. That's pretty far off spec, okay? If we put them in parallel, we're going to have 24 volts at 16 amps. We need 15, pretty close to spec, right? So that's exactly how we run this motor, from 2 24 volt, 8.3 amp, 200 watt panels in parallel. Y'all get that?
It doesn't care about the watts being so off?
Well, the watts is high, you're fine. Your supply is bigger than your demand.
But the panels were 200 watts,
No, these panels are 200 watts.
and the motor wants 360 watts.
Okay, but if you got one 200 watt panel and another 200 watt panel,
Oh, each one is 200 watts?
yes.
Oh.
So to run that motor, we would do this. Right? Tie the positives and negatives together. That gives us 24 volts nominal. 8.3, that's going to be 16.4 amps, which is more than we need. At 400 watts. Got it?
Yeah.
That'll make that motor pretty happy.
So
Pretty close.
what's the difference between an AC and DC motor? Is it just like an AC motor needs the inverter or like a constant stream, and a DC motor is more tolerable to fluctuations in power?
Well, what you just said is sort of true, but we have to step back a minute. So what a motor is something that takes electricity and makes it into mechanical motion. There are hundreds of different kinds of motors. Hundreds, no joke. So within DC motors, there's a bunch of different kinds of motors. Within AC motors, there's a bunch of different kinds of motors. There are motors that run AC or DC. So it's really kind of complicated. For our purposes, they're really, do y'all want to talk about motors now? Or should we kick that down? I think I want to kick down the motor thing.
Yeah, because we're at 15 minutes.
Yeah, I want to do series just because we're talking about series and parallel. Let's talk more about motors later on. What we'll do in the next workshop is actually bring a DC motor in. We'll open it up and you'll see the inside of the motor. And then that's really cool because a DC brush motor is actually a super simple motor. This motor is a little more complicated. All right, now the actual high voltage rack we have at Living Energy Farm. 1, 2, 3, 4, 5, 6. Is 6 panels.
It's a nice rack.
Nice rack. 6 panels. Each panel is about 30 volts. Each panel is, what's 1400 divided by 6? I remember the wattage on these things.
230.
230 watts, 8 amps. All right? 6 panels, 30 volts, 230 watts each panel. The watts is for each panel, not the whole rack. 8 amps. Got it? Now, most of the motors we run are 180 volt. So that's what it does. Plus the minus, the plus, the minus, the plus, the minus, the plus, the minus. When you get to the end of the line, you've got 180 volts at 8 amps. Got it? That's the highest voltage for which you can easily buy cheap industrial motors. So most of the modern grid tie systems these days are running anywhere from 180. I don't think they go much above 360, but I think they're running a lot of them at 360. The advantage of high voltage is the size of the wire. Remember, amperage is what makes heat. And if you've got a lot of amperage, you have to have a bigger wire. Well, if it's a starter wire on your car, your battery's right here and your starter's right here, it's a cable as big as your thumb, that long. But if you're going hundreds of feet and you got some big cable, it gets expensive. So that's the reason they've jacked the voltage way up on these things. The higher the voltage, the smaller the wire, the cheaper the installation, generally speaking. But 180 volts can kill you, so don't mess with it. We run a lot of equipment at 180 volt. The amazing thing about DC versus AC motors, and we started to talk about motors. So an AC motor, step motor, that's the electricity on a sine curve like that, 120 volt motor has about a 10%, any AC motor is going to have about a 10% voltage fluctuation to keep it happy. So 120 volt motor is okay at 110 volts. 100 volts, you wouldn't want to go much lower than that. Our 180 volt motors at Living Energy Farm will run from 50 to 250 volts. That's what this rack will put out. You remember those numbers from this PV panel, the VOC and all of that? Well, the VOC on this rack is 250 volts. So on a bright sunny day like today, if you turn everything off, you go put the voltmeter, it's 250 volts. You turn on a small motor, that 180 volt motor is getting hit with 250 volts, and it's okay. It just starts up and runs. On a cloudy day, when we're overloading the systems and the motors are slowing down like a truck going up a hill, it'll sag all the way down to 50 volts, and those motors are still running. This is the miracle of DC power systems, that tremendous power fluctuation. Yeah. Is that a question?
Yeah, I was just curious. So, like, if you want to add a new machine to the shop, you have to consider like more the amperage because you know they can tolerate swings of voltage. But the amperage, like this motor that used to run your pump at 15 amps, if your max is 8 amps, then it wouldn't be that happy, or is that close enough?
You don't want to push it too far, particularly with the amperage. So a kilowatt and a horsepower are close enough that this rack is about 1.5 horsepower. So basically, like if I found a 3 horsepower motor that wanted 20 amps, it's just not going to run off of this system, basically. You can only push it so far. But in terms of, I want to do a whole other section on looking, because the motors have a sticker just like PV panels do, and there's a whole bunch of crap on there that tells you horsepower, amperage, and understanding all that language is useful, particularly when you're planning for motors. But what you need to know now is you have options in terms of how you set up your power system. And basically for a motor, you have to come pretty close to matching both. If you've got a 24 volt motor and that needs 10 amps, you need to come pretty close to both of those numbers. You know, if you got 20 volts, that's okay, 8 amps, that's okay, but you wouldn't want to put like 60 volts at 2 amps. I mean, you can only push it so far. So in terms of planning motors for the shop, and it's okay with amperage, you can have as much as you want. The voltage, because the amperage is almost like it's passive, it's just there waiting to be used, whereas the voltage is what tries to force its way through. So if I have a motor that uses only 1 amp, in fact most of our motors do, at 180 volts, that's fine. It's only using up 1 amp, doesn't mind, it's made to run at the 180 volts, that's fine. But you know, in terms of planning a new motor, I wouldn't want a motor too far off the voltage range. Although you can get away with a lot of stuff. The other thing that we do with our rack that you can do, you can combine series and parallel things. In fact, if I were setting this rack up from the beginning, and in fact our rack is now set up with a switch in the middle where I can make it do this. Okay, so this is 3 panels instead of 6 in series. So that gives me 90 volts, right? 30, 60, 90. 90 volts. Still at 8 amps, but only at 700 watts because I've only got half the rack, right? But then if I do the other half the rack the same way, okay, now this drawing is a little inaccurate, I'll tell you, if there's any, okay? So these are in series in parallel with those, get it? It's like this becomes 1 power unit, this becomes 1 power unit. So what we end up with, this one up here is 180 volt at 8 amps, 230 watts. I didn't write the 180 volt. This rack down here is 90 volts, 16 amps. It's 230 watts per panel, 1400 watts for the whole panel total. 16 amps. Still 1400 watts total. See how we did that? Tie those 3 together in series, tie those 3 together in series, and then I got my positive wire and my positive wire, tie those 2 together, negative wire, tie those 2 together, gives me 90 volts at 16 amps instead of 180 volts at 8 amps, both of which come out to about 1400 watts. Got it?
Wow.
What that lets us do, again, back to the motors thing, so a circular saw, a household circular saw, wants 120 volts at about 16 amps. Now DC, because it's a constant pressure, actually has a little more oomph to it than AC does. In fact, one of the big uses for DC in the modern world is massive machines. Freight engines, coal trains, the big freight trains that run down the track, those have DC motors. Because if you think about a freight train sitting dead still on the tracks, it's got to start those wheels turning, and then it wants to take that train all the way up to 80 miles an hour. What that means is it needs to have full torque across a huge range of speed. You'd have to have this massive transmissions, all kind of gears. The big mining trucks, you know, a truck that's like twice as big as a house that they put in the uranium mines and coal mines, those things have the same configuration. They've got a diesel engine. I think the diesel engines on the freight engines are like 8,000 horsepower or something. Thousands of horsepower in a diesel engine, a big DC generator bolted right onto the back of the big diesel engine. Big power cables going down to DC motors in the wheels. Because a DC motor can start from a dead stop, it has torque, and then it can go up to full speed and maintain constant torque on the whole speed range. So what we do with our motors, a very small version of that, so we run our 180 volt shop motors this way, but a household circular saw. So it's made to run at 120 volts AC power, but it happens to be a universal motor. Again, all these wackadoodle kind of motors, there's a bunch of different kind of motors. Well, a universal motor is just as happy with AC as it is DC as it is AC, but the speed of a universal motor is set by the voltage. So a normal circular saw, you can run it from this configuration down here. It's getting hit with 90 volts at 16 amps. It's looking for 120 volts at 16 amps. Well, the 90 is close enough, and the 16 amps is close enough. It runs great. It runs basically exactly the same as if you're running it on AC power straight off the PV panels. Yeah.
Just trying to understand the switch when you switch it from 180 to 90. Is it just stopping having half, or is it actually somehow crossing so that instead of the positive to the
I can
negative,
draw you the
it's
switch,
positive
but
to
I
the
warn you, it will
positive?
only confuse you more.
I'm just trying to, is it switching the positive to the negative? Or something?
It's more complicated than that.
Okay.
It's called a double pole, double throw. It's a switch that does this, and the wires crisscross. I can draw it, but I promise it would confuse you more than, it would just make things more confusing. But it just takes this and changes it to look like that with just the flick of a switch. Boom. And you get two sets of energy sources in series, in parallel. I will say one other thing in closing. The other important thing to understand about series and parallel, and it's true for basically any circuit, going back to our water metaphor, so water always goes downhill, always. Well, electricity does the same thing. What that means is that anytime you have a circuit, electricity is going to go downhill, and downhill means to the weakest point, to the point of crummiest equipment, basically. You know the old-fashioned flashlights that stack up batteries, or even a kid's toy that's got like 4 AA's in it? It doesn't matter actually whether those AA's are in parallel or in series. Let's say, I've seen kids do this, it's so sad. They have like they got 3 good batteries that somebody gave them, and they got 1 crappy battery and think, oh, and they put them all in there. Well, as soon as you turn on the switch, you close the circuit, and that dead battery is the low point. And all the electricity from the good batteries, instead of running the machine, go into the dead battery and warm it up a bit and destroy the other 3 good batteries. Same is true for these circuits. Let's say you've got panels, and you've got one really messed up panel. That's where all your electricity is going. This circuit's not going to work with one messed up panel. Same with a battery. Whether it's this circuit, any circuit I've drawn here, if you've got a power source and you've got one part of that power source that is unequal, you can't stack up dissimilar panels, you can't stack up dissimilar batteries. Now, nickel iron batteries, that's another workshop, are somewhat of an exception because they maintain such a constant power supply. But if you have a 1-month-old lead acid battery, that's the kind of battery in your car, and you bring it home and you try to hook up a solar system with it, and you put it next to a brand new lead acid battery, you're going to take all the energy out of your brand new lead acid battery and dump it into the one that's a few months old, because those things decline so quickly that the one that's only a few months old is going to have lower voltage, and the electricity goes downhill to the low voltage point. I've done this before. Again, I can't do this sitting here. But remember I said we run this motor? So we put this motor on 2 PV panels. The panels are in parallel. We throw the switch. This is the switch. Go boom. And the motor takes off full speed. Remember, yeah, this is what we do at our workshops. And then I reach out and put my hand in front of the panels. At that point, I'm blocking 5 or 10% of the PV panel, and this motor drops to about half speed. Same problem. Electricity is going downhill. You're taking part of that panel and reducing the voltage, and your voltage just goes there instead of going to the motor. Which is just to say that when you're thinking about series and parallel circuits, you've got to make sure the whole circuit is uniform in terms of power supply, resistance, voltage, all of that. It needs to be uniform. If you have 2 different sets of PV panels, they have to stay separate sets, basically. Use them differently, or live with the fact that you're going to have a horribly inefficient system. Have we done about an hour?
Yep, it's an hour.
All right, workshop number 1.
Yay!